Maybe just wait 10 or 15 seconds to make sure everyone gets in okay. Okay, so hi everyone. Thank you for joining the AGU Atmospheric Science Early Career Seminar Series webinar that we have today. My name is Ren Smith and I'm a member of the AGU Atmospheric Science Early Career Committee. I'm just going to open with a really quick introduction to the committee and what it does, and then I'll hand it over to the moderator to start the seminar session today. So in essence, the AGU Early Career Atmospheric Science Committee is a committee that provides resources for and creates and promotes professional activities for early career scientists in the atmospheric science discipline. We have a number of events that are planned this year. There's a couple here that are listed on this slide, the ones that are coming up soon. In mid-April, there's going to be a webinar on creating an effective DEI committee. In late April, there's going to be a panel on careers in government and research labs. And then for these seminar series, or for this seminar series, we're hoping to host 3 or 4 more of these seminar series in 2023, and are going to be soliciting some new abstracts soon. So keep your eyes open for a call coming out soon. If you have any questions, comments, concerns, etc., anything like that, feel free to send an email to the committee at the ec.atmossci@gmail.com email address here. And then the last note that I put on here to make sure I didn't forget is just to let everybody know that this meeting is going to be recorded. So with that, I'm going to turn this over to our moderator, which is Brian Toon, who's a professor in the Department of Atmospheric and Oceanic Sciences at the University of Colorado Boulder. So I wanted to say publicly thank you to Brian for being here today and for agreeing to moderate. And with that, I'll turn it over to you. Thanks.
Thanks, Ren. It's really exciting to be involved in this early career presentation. It's a great opportunity for young people to present talks outside the AGU meeting where there's 30,000 people. So let me start with Kelsey Malloy, who received her PhD in atmospheric sciences from the University of Miami Rosenstiel School in 2022. And currently she's a postdoctoral research scientist at Columbia University, studying subseasonal to seasonal predictability of severe convective storm risk, as well as how the climate change may be impacting that risk. She's also interested in understanding monsoon forest teleconnections as a source of subseasonal to seasonal predictability for U.S. rainfall. Outside of research, Kelsey is a founding member of Seasoned Chaos, a science communication blog for climate forecasting topics, and has been involved in many science outreach projects and groups. So go ahead, Kelsey.
Great, thanks, Brian. I just want to check everyone can hear me, see my screen. Okay.
It's good.
I'm going to assume yes. Great. Okay, great. Thank you. I also want to take the time to thank the AGU Early Career Committee for inviting me. I'm really excited to talk about some work that I have done. Today, I'll be talking about using causal networks to understand subseasonal Great Plains rainfall predictability via remote teleconnections. This is some work that I've done for my PhD with Ben Kurtman at the University of Miami Rosenstiel School, and currently I am a postdoctoral research scientist at Columbia University. One of the main motivations for this work is that forecasting on the subseasonal to seasonal timescale, this is called the S2S timescale, skill for predicting rainfall is very low, especially in the summer months. So if we were to consider forecast skill for forecasts going out a certain number or certain time frame, we would see that we have relatively high skill for the weather timescale and the climate timescale. But there's this desert of predictability between these two timescales. We consider this the subseasonal timescale, and instead we have to rely on forecasts of opportunity. This phrase is used for the idea that there are times where forecast scale is relatively higher, or we have higher confidence in certain forecasts when there are certain predictors present. So for example, El Nino Southern Oscillation can be used as a forecast of opportunity for temperature and rainfall anomalies, for example. In the summer months, however, we often try to understand predictability through quasi-stationary Rossby wave activity, since it's been found to be influencing climate extremes during this season. In particular, I'm going to talk a lot about the East Asia monsoon as an example, and this has been shown to influence US rainfall patterns on the seasonal timescale. So in previous work, Loy and Kurtman 2022, we have found that on the seasonal timescale, the East Asia monsoon can influence precipitation patterns. So I just want to kind of demonstrate that with this figure here. So here we're seeing a difference composite strong minus weak East Asia monsoon precipitation patterns. We can see this monsoon circulation. And so we see this wettening in this kind of rain belt here, consider the East Asia monsoon. And then I just kind of want to also point out that the West North Pacific monsoon is another system that is typically out of phase with the East Asia monsoon. So we have this monsoonal circulation. And we can see it's also associated with precipitation patterns, including rainfall anomalies over the Great Plains region. And this has also been demonstrated in model studies like in Zhu and Lee 2016. They applied heating in the East Asia monsoon region and found that it can produce this Rossby wave pattern that influenced circulation and rainfall over North America. But we have a really simple question about whether or not this teleconnection also operates on the subseasonal timescale. So monsoon variability also operates on this subseasonal timescale. We call this the boreal summer intraseasonal oscillation. The idea is similar to the Madden-Julian oscillation, where we have these regions of active and inactive convection propagating, but mostly in this northeastward direction in reference to the monsoon variability. And so we want to understand if we can really have this link kind of become, or really quantify and identify any causal links between these regions of subseasonal monsoon variability and Rossby wave activity or US rainfall variability. But before we understand causality, let's just kind of take a look at what these rainfall events look like. So what we're going to do is we're going to take the averaged rainfall in this Great Plains region and first correlate that with anomalous OLR and Z200 fields. So this is understanding patterns in convection and upper level circulation. So we can see that Great Plains rainfall events are associated with active convection over Great Plains, probably not surprisingly. And then if we look over the monsoon region, we have very weak, but we have this active convection over the East Asia monsoon region. We also see in terms of circulation, this propagating wave train pattern over the North Pacific into North America. So these are patterns associated with these Great Plains rainfall events. But we can also look at these anomalous fields from 10 days before the Great Plains rainfall events. So really I want to highlight, we have these this active convection over the East Asia monsoon region still, and also these dry anomalies over the West North Pacific monsoon region. We also see that we have our wave train that's more centered now over East Asia and the West North Pacific. So this really suggests that Great Plains rainfall is linked to cross-Pacific Rossby wave activity, and perhaps this Rossby wave activity is linked to monsoon rainfall. However, what we really want to do is try to understand if this is true, in the sense that can we really detangle these rainfall patterns over these particular regions as being drivers for this Rossby wave activity. And what we're going to use are causal effect networks. So data-driven methods are becoming increasingly more popular to understand physical links in the climate system. So the idea is that we're going to use this algorithm that's going to try to kind of tease out these relationships. So we have these common issues when we're trying to detangle correlation and causation, autocorrelation, indirect drivers, common drivers. And the idea of the algorithm is that if we have our variables of interest that we know might be interrelated, and they have their own respective time series, what the algorithm does is essentially perform iterative conditional independence testing in order to kind of create this reduced set of parents, or kind of these different connections between the drivers. And the idea of the NCI part of the algorithm is really just to then perform independence testing on the parents of the parents in order to kind of create this reduced set of drivers that are connected to each other. And then the last part of this network is to visualize or interpret these resulting links. So really to quantify these links. So I'm just going to jump into it to kind of try to understand or explain this further. So we had seen that we had this these regions of active and inactive convection that might have been related to our regions of circulation. So here we have these two low pressure systems that are related to these or possibly related to these regions of active and inactive convection. So what we can do is put our West North Pacific monsoon rainfall, East Asia monsoon rainfall, and these two features that we see into our network. And where you see the dotted lines in between the different nodes are considered contemporaneous links. So these are just correlations that we cannot really discern or distinguish any causality, but we know that they're related. And then where you see the arrow, we can read it as such. So if there's a 1 standard deviation increase or strengthening in the East Asia monsoon low, we can expect a 0.36 standard deviation increase or strengthening in the North Pacific low feature 1 week later, because we're looking at weekly anomalies here. So the idea here is that in this network, the East Asia monsoon low feature is really important for kind of starting that Rossby wave activity. However, I just want to point out that we do have these contemporaneous links. So we really need to understand whether it really is the West North Pacific monsoon rainfall or the East Asia monsoon rainfall that's really important for setting these patterns in the North Pacific, since they're both connected to the East Asia monsoon low through this kind of network. So the idea is that we're going to use causal maps. So that means we're going to take two time series that are interrelated. So here, the West North Pacific monsoon and the East Asia monsoon. We have our 3D time series fields. So here, we're going to use Z200 and OLR. These are one-dimensional at every grid point. So we can take every grid point, quantify a causal link with our different monsoon drivers, create these kind of maps then, and then we can use the patterns from the causal maps and compare them to those original correlation maps. So for example, here's the causal map for Z200 based on the West North Pacific monsoon rainfall. So the idea here is that this is the Z200 response to the West North Pacific monsoon from 1 week before, so the rainfall from 1 week before. And the idea is that we're conditioning out the East Asia monsoon rainfall. So these patterns should only be due to the West North Pacific monsoon rainfall, not the East Asia monsoon rainfall. So we can see that the response is mostly confined to the tropics and subtropics, at least when we compare to the East Asia monsoon rainfall. So again, this is the Z200 response to the East Asia monsoon rainfall from 1 week before. And the idea is that we are conditioning out the West North Pacific monsoon rainfall here. So here we can see that we have a more mid-latitude response. And really what we would want to do is compare that to our correlation maps that were related to our Great Plains rainfall events. And so we can see that the causal maps for the East Asia monsoon rainfall are very similar to the patterns we had seen for the Great Plains rainfall correlation maps. So the East Asia monsoon rainfall better explains the triggering of this Rossby wave activity that's related to these Great Plains rainfall events. Similarly, we can do this for OLR. So here in this top panel, again, this is the OLR response to the West North Pacific monsoon rainfall from 1 week before, conditioning out the East Asia monsoon. So again, we have mostly a response in the tropics and subtropics and perhaps the Southeast US. And we want to compare that to the OLR response to the East Asia monsoon rainfall from 1 week before. And again, we want to compare this to our correlation maps to really understand whether these causal maps are related to what's the Great Plains rainfall events are related to in terms of patterns. And we can see that the East Asia monsoon rainfall is better explaining this convection over the Great Plains region. So overall, as a summary, I just want to show the correlation maps that are related to our Great Plains rainfall events, as well as the causal maps from our East Asia monsoon rainfall specifically. And we can see that there are similarities between the two. that cannot be explained by any of the drying from the West North Pacific monsoon region. So overall, the East Asia monsoon can kind of force a teleconnection that's related to US rainfall variability. This had been shown on the seasonal timescale, but we were also able to show that this might be important on the subseasonal timescale as well. So perhaps subseasonal monsoon variability, especially anomalies over the East Asia monsoon region, may be an important forecast of opportunity in order to understand forecast skill in the summer months for rainfall, or to assign confidence in certain forecasts. And then also I also demonstrated that causal effect networks and causal maps are an important and possibly effective tool to disentangle correlation and isolate different teleconnection forcings and their responses as well. And at this point, I can take questions, or we might be waiting to the end. I also wanted to leave my email, website, and here is a QR code if you want to read the paper as well. Thank you.
Thank you, Kelsey. I see you're right on time and very organized in telling people how to contact you, which is great. I don't see any questions on the chat yet, but so let me ask a question. You know, obviously people are concerned about blocking systems setting up and causing some persistence in no convection or convection, whichever way it goes. So how does your modeling interact with blocking?
Yeah, that's a good question. I think there has been like a lot of research on whether the NAO is related to blocking, but I've mostly seen that in relation to European patterns, or really Euro-Asia precipitation or temperature patterns in the summer. I think for the summer months, blocking is in terms of like literature, I've seen that blocking is not as prominent for understanding Great Plains precipitation. But in terms of heat waves, the East Asia monsoon has been shown to be important for as a teleconnection for kind of setting up these preferred, regions of heat wave frequency. So hopefully, does that answer your question for the most part? I haven't seen it in a subseasonal timescale though.
Okay. Looks like I'm seeing some questions here. So Michael Diamond asks, it's a very nice talk. It looked like the causal estimate is much weaker than the correlation for both OLR and Z200. Does this suggest the causal effect is real but somewhat weak, or would the addition of more or better information increase predictive skill?
Yes, so that's a good point. So the causal maps suggested that it is a pretty weak relationship, but these are all performed with statistical significance and false discovery rate methods. So the idea is that these are still, statistically significant relationships, albeit weak. I think it still remains to be seen. I think future work will have to look in S2S models, forecast models, to really see if this is even though it seems to be a source of predictability, whether or not it is related to increased forecast skill during, let's say, East Asia monsoon, strong East Asia monsoon rainfall events, and whether that does lead to increased forecast skill of rainfall over the US. That still is an ongoing region of research. So that's a really good point, though. These are still pretty weak, at least even compared to, let's say, winter MJO teleconnections as well. But it's still, summer is a very challenging season to predict. So it seems to be very promising. But thanks for your question. Good one.
Okay, another question from Ben Nault is, how have the extremes from polar vortex / jet streams potentially impact this?
Yes, so I think that is mostly, at least in terms of my research, mostly confined to cool season rainfall and temperature anomalies. I haven't seen much work on how polar vortex variability can influence summer patterns, but it does seem to be really important if we're considering, like, for example, springtime, so getting into the warm season. But for midsummer, I think it's probably not as prevalent because polar vortex variability is mostly significant in the winter months.
Okay, I don't see any, let's see, here's another one. Is there a significant relationship between monsoonal rainfall and Western US weather climate?
Yes, so let me actually go back towards the beginning. It does seem to be on a seasonal time scale. This is one of my background slides. So we do see that the East Asia monsoon variability on the seasonal timescale might be related to Western US weather or really climate, so seasonal anomalies. But we haven't tested this on the subseasonal timescale. I mean, I guess let's look at the causal maps real quick. Mostly focused on the Great Plains. I don't think it did have much of an effect. Yeah, maybe very little, but it does suggest that perhaps also the Western US, but it wasn't really much of my focus, but it would be interesting for future work to kind of hone in on this region in particular. So great question, a great observation too.
And one final question here is, it looked like the causal estimate is much weaker than the correlation for both LLR and Z200. Does this suggest that the causal effect is real but somewhat weak, or would the addition of more or better information increase predictive skill?
I think I did answer that question. I think we already asked that one earlier. Yeah.
You're right, this is a repeat.
That was the same one from a little bit ago.
Okay. Well, I'm glad you noticed that.
Yeah, no problem.
Okay. Thank you very much, Kelsey. That was a great talk and really exciting that maybe there's some potential predictive skill here.
Thanks, Brian.
Next speaker is Michael Diamond. And Michael is an assistant professor in the Department of Earth, Ocean, and Atmospheric Sciences at Florida State. He got his PhD in atmospheric sciences from the University of Washington in 2020 and was a series visiting postdoctoral fellow at NOAA's Chemical Science Lab and the University of Colorado at Boulder, Department of Atmospheric and Oceanic Sciences, before joining Florida State this spring. His research focuses on aerosol cloud interactions and their implications for climate change. So take it away, Michael.
Awesome. Thank you so much for the introduction and to the organizers for having me speak today. I'm really excited. So my talk today is going to focus on a couple of pieces of recent work, thinking about how both inadvertent and also deliberate aerosol perturbations can teach us about Earth's climate and what we still need to learn about these perturbations to better understand present climate change, and also thinking about some potential future ways to reduce maybe some impacts. So the way I like to start for talks like this that touch on this concept of climate intervention that I'll mention in the next slide is where we're currently at with our policies to limit climate change or limit global warming on the emission side. And it's kind of a good news, bad news story. The good news, which I like to start with, is we're looking a lot better, or things are looking a lot better than they did 10, 15 years ago. Back then, we were probably on track in a quote unquote business as usual sense to be on target for 4 degrees, 5 degrees, or even more of warming by the end of the century. But since then, renewable energy prices have gone down. We've had the Paris Climate Agreement and amendments to that, and things look a lot better. So from this estimate here, which was at right around the time of the Glasgow climate meeting in 2021, the suggestion was current policies put us on track for 3 degrees Celsius. And if you read optimistically into what countries said they were going to do and what businesses said they were going to do, you could maybe get lower, but not quite to the 1.5 degrees Celsius goal. So that's the good news. The bad news is that 3 degrees Celsius is still extremely bad. It's good compared to 4 or 5, but it's not good in general. So because of that, and because of kind of this last mile problem, how do we actually get temperatures down to where we want them to be? There have been increasing suggestions that one temporary measure we could do is something called solar climate intervention or solar geoengineering. Different terms exist for this. But the one of the kind of more mainstream ideas for this would be as a temporary measure while you allow mitigation. So here represented by this black curve of decreasing climate impacts first by doing the most obvious thing, which is to stop the problem at the source, stop emitting CO2. Then carbon dioxide removal. So the idea of taking carbon from the atmosphere and bringing it back under the ground. We currently don't have ways to do that at scale, although there's very promising avenues that hopefully we'll be able to scale up. So while that's scaling up, the suggestion is we could maybe directly reflect some amount of sunlight and decrease some effects of global warming that way as a temporary measure to keep temperatures from going above 1.5 or 2 degrees Celsius or whatever target you may want with that. And that's something that has been very controversial in the research community, but has recently been garnering more kind of serious attention from the US government, at least, and governments around the world. There's also a UN environmental program report that just came out. But this is a figure from the National Academy's report that was released in 2021, focusing on 3 of these different techniques. Probably the most famous is the stratospheric aerosol injection idea, where you put aerosol up in the stratosphere to reflect sunlight. We're going to focus today on this idea of marine cloud brightening. So can you increase scattering by clouds over the ocean and offset temperatures that way? This is an idea that actually has a surprisingly long, or it's been proposed a surprisingly long time ago, at least for me. I was kind of surprised when I saw this paper from the 1960s. This is the first paper that identified what are called ship tracks. So you could see them pretty clearly in this astronaut photo from the International Space Station from just a few years ago. Or here, this is the first satellite image of them from the TIROS-7 weather satellite. And there are these kind of curvilinear features in the clouds that we now know follow individual ships. And even in this first paper, there's kind of this throwaway paragraph in the conclusion that because they've identified these features, it should theoretically be possible to artificially increase cloud albedo. And back then, we didn't know the exact mechanisms. Since then, in part from studying these ship tracks, we've learned a lot more. So the way this works, kind of the first most fundamental effect is called the Toomey effect. So you imagine you're out over the ocean. There's not much pollution sources around. You just have some sea salt kicked up by the wind. You could create a cloud, assuming you have some amount of liquid water with which to create your cloud. What you could do is you can create a cloud with a relatively small number of relatively large droplets. Now, your ship goes by, it's emitting a lot of aerosol particles in the smokestack. And now, cloud particles need one of these cloud seeds, one of these cloud condensation nuclei to actually form. So you could form a cloud with the same amount of liquid with a much larger number of much smaller droplets. That increases the effective surface area, leading to a brighter cloud and more sunlight reflection, and therefore a cooling effect overall. The assumption of constant liquid water path is doing a lot of work in that. So there are also possible adjustments. So you can get suppression of drizzle. So for these clouds natural clouds over the ocean, these relatively few large droplets are pretty good at glomming together and forming precipitation-sized droplets and falling out due to gravity. When you have a larger number of small droplets, they're less good at coalescing together to form these precipitation-sized droplets. So you can imagine you now have clouds that maintain more water or maintain themselves for longer as they go across the ocean. So that would be an additional cooling effect. Versus you can also have, for a couple different reasons, when you have more small droplets, especially near cloud top, enhanced turbulent entrainment of dry air from above the cloud down into that cloudy layer that dries out the cloud. So a warming effect that partially counteracts the other two. So in part because of those adjustments and the fact that they have different signs, this is still really uncertain overall. And actually, if we're thinking about the energy imbalance due to human activities, aerosol cloud interactions are the single largest source of uncertainty in that. So, well, one, why do we still kind of have this uncertainty? So I'll talk about coming up some of the reasons we have this uncertainty still, even though we have used great natural experiments in the cloud field. And then what do we need to learn if we're actually thinking of maybe harnessing this effect to our benefit? If it's so uncertain, can we actually even do that? So for part one, we're going to talk about at least one part of this problem, which kind of rolls on the detection side. So what have we learned from inadvertent international shipping pollution perturbation? So we've been able to test these hypotheses really well with it, but somewhat surprisingly, when we try to scale this up, at least prior to some more recent work, we haven't had much success at actually finding a big global signal from ship tracks. So this paper back from 2007 took 1 year of painstaking manual identification of ship tracks. And when they kind of did that manual detection and compared the brightness of ships in those tracks to outside, they found a global forcing of only a fraction of a milliwatt. So really nothing globally. And that's, you know, okay, maybe like they're great for testing hypotheses, but they don't matter globally. But that's a little bit surprising because if you put shipping emissions into a global or regional climate model, what that climate model suggests is the cooling should be 2 to 3 orders of magnitude greater than what you get from those detected ship tracks alone. So the possibility here is that these easily detectable ship tracks are just the tip of the iceberg, and we're actually missing a lot of the more subtle effects. Maybe we could do something more climatological. So Peters and colleagues looked at air parcels as they were going towards a shipping corridor, and then after they've passed the shipping corridor and presumably more polluted, which was a really clever way of doing things, but they were also unable to detect significant changes in the clouds using this method with only a couple of years of data. And when they did this again in a climate model, they found the same thing. Even though you know the answer in the climate model, the atmosphere is just too noisy to get a signal on those short timescales. But, and that method, really importantly, required the air to be going perpendicular to the shipping corridor. But there's one shipping corridor that kind of has the opposite situation. In the Southeast Atlantic here, you could see the shipping corridor and the yellow shipping emissions. And the winds here, these are low-level wind barbs. The winds are pretty much perfectly parallel to the shipping corridor, meaning that they're constraining the pollution relatively nearby. And if we look at satellite-detected cloud droplet number concentration, you can kind of see here, it basically looks like there's a line going through the low cloud deck over here in the subtropics. So we figured, can we use that information to try to get an estimate of the shipping effect? And the method we used here is called universal kriging. I won't go into the full details here since it's a short talk, but basically we pretended that the shipping corridor is bad data, mask that out. And can we interpolate over it with the unaffected nearby clouds that should have relatively similar meteorology, but just don't have that shipping corridor. And because the winds are keeping that pollution constrained, the pollution really should be just within that area. So when we do that here, this is kind of our factual situation. So what we actually see from reanalyses or satellite, you can see in the sulfate here, pretty clear shipping lane, and something that looks like that in the cloud droplet number concentration effective radius. So now we can create our counterfactual situation called no ship here, using that statistical technique, and importantly, get the difference here. So in that difference, really excitingly, especially in the subtropical section, we get about a 5% increase in cloud droplet number concentration, 2.5% decrease in the average size of those cloud droplets, extremely statistically significant by a couple different ways you could measure it, which is really exciting since the first time we were able to do that at this regional climatological timescale, not just at this individual track level, but importantly, does that scale up to radiation? And just to kind of skip straight to the punchline here, in the purple, black, and gold here, there are a couple different ways of measuring it, either going straight from the cloud brightness and estimating what that should mean for the top of the atmosphere radiation, or the gold here, looking at the top of the atmosphere radiation directly. In both of those, you get about 2 watts per meter squared of local cooling over that shipping corridor, which is 1 to 2 orders of magnitude more than what you'd get just from manual track detection. So great, it's solved, right? We know that this has a big effect and we can just do it everywhere. Not quite. So if we're thinking about these proposals for marine cloud brightening, this is work that we published last year, thinking about a roadmap for what do we need to understand better about to know, at least on the technical side, whether or not marine cloud brightening would be feasible, and what could we find that would tell us definitively that it's not feasible and that it's not a worthwhile research endeavor. So this is kind of a schematic of our roadmap down here, where the way we're thinking about this is we have these different disciplines, information from different disciplines. So physical science is where I am nested and most comfortable, but we also need input from technologists, ecologists, social scientists, and ethicists to be able to assess this. The way we're organizing it here is we have these, what we're going to call checkpoints. These are essentially relatively self-contained science questions where we would need answers to these open questions to be able to tell whether or not this is feasible on the technical side. So as long as none of the answers are yet no, you disseminate information to policymakers, you keep the research process going. But the way we've structured this is we're kind of considering each of these checkpoints as a necessary but insufficient criteria. So if you answer yes to any of them, that doesn't mean yes, go and do it. But if you answer no to any of them, it does mean that it wouldn't be feasible, and therefore you don't need to keep research on the other checkpoints because you just know the program is not feasible as a whole. So that's a little bit surprising and kind of stark, right, to just completely shut down a research program. And this is because of something called lock-in, or the concern here is something called lock-in. So this is a recommendation that comes straight from the National Academy's report from spring 2021, that you should have these quote unquote exit ramps or criterion protocols for terminating research programs or areas as part of the research to kind of break this lock-in process where there's a couple different ideas of what this might be, but basically you could have self-perpetuation of the research program through kind of creating this research community, creating patent holders, creating interest groups and institutional momentum. There's also this fear of a slippery slope from research deployment. I should mention all of these are kind of controversial in the literature, but our argument here is that through kind of this self-governance idea of identifying these checkpoints and hopefully bringing them explicitly into a future funding program, you can allay some of these concerns. So the way we have this out, we have these 6 checkpoints. So generation delivery, exit if it's infeasible to generate and deliver particles of the proper size, local cloud adjustments. If you do get into the clouds, you need to have more of those enhancing adjustments, not the detracting adjustments from entrainment. The clouds that are susceptible to brightening have to exist at a scale to actually get the brightening you need. If you need to be able to detect that brightening at some kind of time scale to allow you to adjust in response to new conditions or concerns. And then thinking about impacts both at the local scale for marine ecosystems and coastal communities and the global scale, like what Kelsey was just telling us about these kind of wave responses. If you have cooling or some kind of perturbation in one region, we know from the atmosphere, it doesn't just stay in that region, it'll have wave responses throughout the atmosphere. And I went a little bit slow, so I'm gonna go straight to this idea of bringing in the transdisciplinary nature. So for all of these checkpoints, they require thought from physical science. Many of the questions are physical science questions. For some of them, like this local cloud adjustment, is essentially just a physical science question. When you start getting into questions of especially the impacts, both locally and remotely, a lot of these things are thinking about taking an exit ramp if you have a dangerous impact. And there's actually no science definition of dangerous. You really need social scientists, ethicists, and ecologists to say, okay, the physical science tells us there's this change in precipitation, but what does that mean for ecosystems? What does that mean for communities? And how do we weigh an impact in one region versus another? We really need to have multiple people at the table to be able to kind of bring that together. So with that, I'm going to leave up this roadmap. Thanks so much for listening, and I'm excited to take your questions. Thanks so much.
Okay. Thank you, Michael. I'll wait for a few questions on the chat here, but I recently read a paper that argued that ship tracks were not relevant to the larger scale interaction between aerosols and clouds. And I forgot what exactly the argument was, but I believe it was about circulations and within the ship track that were distributing the effect beside the ship track, canceling part of it.
Mm-hmm.
How typical do you think ship tracks are of the general problem of aerosol?
Yeah, that's a really good question. And I'm not sure exactly which paper you're thinking about, but there is some modeling work from Hailong Wang, at least, and others, suggesting that in certain mesoscale configurations, you can get these secondary circulations where you'd get, so if you have a ship track kind of going through more open cellular convection, where you kind of have these hexagons with an open middle, you can fill those in right on the ship track, but essentially kind of erase clouds along the sides. So if you have some method where you're just looking in the ship tracks and comparing it to clouds right next to the ship track, you might be falsely estimating a big increase in cloudiness and cloud brightness when you're actually just redistributing where the cloud is. And that's something that does concern me, especially on individual ship track studies. I think that for the kind of regional climatological view that I took in part 1 in the Southeast Atlantic, that should kind of come out in the wash when you're looking at these relatively larger areas that kind of integrate over a lot of different ship tracks. But I think it is the big concern for individual tracks. And I would also say there's, unfortunately couldn't include it in this relatively short talk, but there's some really interesting new work, both looking at machine learning detected tracks that can get you orders of magnitude more tracks than you can get by hand, and also just tracking emissions from individual ships. And those seem to suggest that you can actually get much bigger liquid water path positive responses than what we see from other lines of evidence. You don't seem to see those in other ways of getting at climatological aerosol cloud effects in these more decoupled trade cumulus layers. And I think an open question is that because of a bias in kind of secondary circulations biasing the effects in individual track experiments, or is there just a fundamental physical difference between an isolated plume and a more climatological background that means the physical effect is actually just different?
Okay, it seems like our chat's not functioning quite right here. But so let me ask another question along the same line. I think the case you showed, the wind seemed to be aligned with the direction of the ship track or the shipping lane, which I thought was very interesting. And so you wonder whether the fact that more general examinations of the correlation, perhaps the wind was not along the direction of the ship track. So maybe something about either the physical effect or the detectability depends on the wind being aligned with the emissions, which you would think would tend to make them last longer, the impact would last longer. So I guess if you looked at that wind direction ship track correlation.
Yeah, I mean, my kind of thought for why you don't see this as well when you kind of did this perpendicular method is you're essentially just kind of spreading out the perturbation really thin, which from a physical perspective might actually be more efficacious because you're not these are all kind of, they scale sublinearly, of course, so the more aerosol you add, you're not just keep on getting a linear increase in brightness. So it might be kind of, you might actually be getting more ultimate brightening from those, but it's much harder to actually detect any of them because they're kind of spreading all over the place, versus when the wind is constraining it, you have all of your effect happening in one area. That makes it much easier to detect, even if it's not the most efficient way to actually get the brightening. One thing we do want to do, and fingers crossed we'll be able to do in the next few years, is compare this kind of climatological view here from individually detected tracks from machine learning in this area, and see if we can kind of get convergence between this kind of top-down statistical method and a bottom-up compilation of individual tracks when we're able to go beyond the manual detection, but actually to that automatic detection that gives us a lot more information.
Okay, great, Michael. Thank you for that really good talk. And this is obviously a very important area of aerosol cloud interaction research that needs a lot more work. So we have to move on now to Minnie Park. Minnie Park is a postdoctoral research associate at Brookhaven National Lab. She received her PhD in atmospheric science in 2020 from Colorado State University, where she looked into environmental controls and aerosol impacts on tropical sea breeze convection through cloud resolving model simulations. And following graduate school, she's been using remote sensing and in situ measurements from field campaigns and focusing on joint variability between aerosols, clouds, and large-scale meteorology. Go ahead, Minnie.
Thank you for the introduction. Before I get started, I'd like to acknowledge the co-authors of this work, Alison McComsky and David Peinema, and the funding support from the NASA Activate project. So our work started with this one figure here in the upper panel. This is the decadal trends of aerosol optical depth at 550 nanometer from 2003 and 2020. And here in this figure, blue shading indicates a decrease and red shading indicates increase in the AOD over the last 18 years of Aqua Modis record. The cross hatches mark here in the mark statistically significant trends. So while many interesting features exist, I'd like to draw your attention to this magenta box, the eastern seaboard of the United States, where widespread of blue shading is, probably due to the clean air policy, and it's like that, not that surprising. Then looking into the deseasonalized time series over this area, as shown in this bottom panel, monotonic decrease is evident and robust regardless of the data source, Aqua Modis, Terra Modis, or MERIT-2 reanalysis data. Then what's exciting? Well, this increase in AOD over decadal timescales provide a long-term experiment in the natural environment to explore how natural or other anthropogenic processes affect the signals and impacts of aerosol cloud interactions. Therefore, here we examine how marine boundary layer clouds have changed over decadal timescales in tandem with changes in aerosol and meteorology, and how this joint variability has affected the surface survey radiation budget. So this work is a part of the aerosol cloud meteorology interactions over the Western Atlantic experiment, NASA Activate project, one of the primary goals of which is to characterize the relationship between aerosol and microphysical and macrophysical properties of marine boundary layer clouds under different meteorological conditions over this area. So Activate study domain, highlighted here with the red box here, where we saw the widespread AOD decrease in the previous slide, is a natural laboratory as many oceanic and atmospheric processes of different spatial temporal scales coexist. For instance, the Gulf Stream current system that transports warm seawater from the Gulf of Mexico to higher latitudes along the coastline of the eastern seaboard of North America establishes a distinct horizontal gradient of sea surface temperature. On the other hand, in the atmosphere, a semi-permanent Bermuda high sets up anticyclonic wind patterns. Furthermore, its fluctuation with the Icelandic low, called North Atlantic oscillations, NAO modulates westerlies and storm track activity from intra-annual to multi-decadal timescales. Besides, as you can see from different colors of arrows here, diverse aerosol sources across the Western North Atlantic, both anthropogenic and natural, and distinct seasonal variations of such aerosols may further convolute the interplay between aerosols and marine boundary layer clouds in this area. Finally, over the Western Atlantic, the mean low cloud fraction is over 20% throughout the year. However, they have not yet been thoroughly examined, unlike those in stratocumulus deck regions. The low clouds over this area do not show a robust correlation with LTS or EIS. And we think this lack of correlation may be linked to the very unique nature of the Western North Atlantic. So to address our goal, we performed decadal trend analysis on monthly gridded fields of aerosols, low clouds, meteorology, and radiation, as summarized in this table. So for the low clouds, we use the Sirius Modis low cloud products. Here we deem a deseasonalized time series of each variable statistically significant when it passes this test called Bond-Kendall test, which examines the monotonic behavior of a time series. So throughout this talk, statistically significant decadal trends are marked with the cross hatches. So let's begin with the decadal trends in the low cloud macrophysical properties, namely low cloud fraction and optical thickness, as shown here, because these two are the primary driver of the cloud radiative effect to the first order. The first figure shows decreasing trends in low cloud fraction across the Western North Atlantic with limited areas of statistical significance. Numbers on the upper right corner of each figure show the range of statistically significant trends over the study domain. And unlike cloud fraction, low cloud optical thickness on the right-hand side shows widespread decreasing trends throughout the domain. While this study focuses on low clouds, I also like to point out that we find very pervasive trends in high cloud fractions across the study domain, as these changes can alter the irradiative environment where low clouds form. Next, we looked into the microphysical properties of trends, trends of low clouds to understand the low cloud optical thickness trends that we just saw in much more detail, and to see whether low clouds exhibit any trends in response to AOD decrease over this area. First, here what's shown here is the cloud number concentration decadal trend analysis results. First, we find significant decreases in low cloud number concentration across the entire domain, where we find substantial reductions in AOD, indicating the negative Toomey effect, less aerosols and fewer number of cloud droplets. And then we look into the liquid water path. Over our study domain, limited changes to liquid water path are found, whereas when we look into the cloud droplet effective radius, pervasive and statistically significant and robust trends are found in here, similar to cloud droplet number concentration on here. Therefore, the optical thinning of low clouds that we saw in the previous slide is attributed to cloud droplets becoming fewer and larger rather than reduced liquid water path, given the resembling spatial patterns and decadal trends. Next, I'd like to present some interesting seasonal behaviors of AOD and cloud number concentration trends. So here, decadal trends of AOD are displayed monthly. Statistically significant decreasing trends are most pronounced and especially widespread in the summer months, especially from May to August here, but those trends are limited in the colder months. Then when we compare AOD seasonality with cloud droplet number concentration here, in warmer months from May to August, especially here, significant trends in low cloud droplet number concentrations are absent over the study domain when the magnitude of AOD decrease is most substantial. So we think that the absence of correlation between AOD and cloud droplet number concentration implies the summertime Western North Atlantic presents an updraft limited cloud nucleation regime. In other words, if the maximum number of cloud droplets have been nucleated already, further changes in cloud condensation nuclei would not be expected to change cloud droplet number concentration. Then what about the colder months? So finally, in the colder months, significant decreases in cloud droplet number concentrations are present over the study domain, especially from October to March, when the AOD decrease is pretty much limited. So the possible explanation for this decrease in cloud droplet number concentration without significant changes in AOD include enhanced evaporation or washout, or reduced cloud activation. Despite these statistically significant trends in low cloud microphysical properties that I've been presenting so far, a corresponding pervasive increase in all-sky surface shortwave irradiance over the study domain is not found. So what's plotted here is from the same period, using the series EBEB data, we plotted the decadal trends of the all-sky surface unveiling shortwave radiation flux. And you see the red shadings here, but the statistically significant trends are limited to the southeastern part of the domain. So altogether, the results that I presented so far imply that neither the changes in low cloud fraction nor the changes in aerosol-induced low cloud microphysical properties are the primary driver of the surface shortwave radiation or cloud radiative effect. So we speculated probably other factors counteract the suggested Toomey effect. Then that's when we decided to look into larger scale meteorological fields, given the importance of the Bermuda High and the North Atlantic Oscillation in this region. So to start off, I'd like to introduce well-known tripolar patterns between the NAO index and sea surface temperature over the North Atlantic, as presented here on the upper top panel. So a patch of positive correlation in the mid-latitude North Atlantic, surrounded by patches of negative correlations here, as you can see by blue shadings here. The NAO SST tripolar patterns imply that SST anomalies over this area region are induced by air-sea heat exchanges and surface winds associated with the NAO changes. So we find similar tripolar patterns in the total precipitable water here and surface heat fluxes as presented here. With this tripole in mind, let's move on to the decadal trends in the large-scale meteorological fields to see actually what happened to these fields highly correlated to the NAO. So first, mean sea level pressure trends here show the strengthening of Bermuda High and with this red shading, and strengthening of subpolar low with blue shading here, implying a greater pressure gradient between these two, and hence more positive values of NAO index. Next, we examine the trends in SST and total precipitable water vapor here. So we see similar tripolar patterns in both fields. So an area of SST warming surrounded by SST cooling, and similar to the NAO SST correlation in the previous slide. And SST warming is across the entire study domain here. Accordingly, decadal trends in water vapor represented by total precipitable water here also exhibit a tripolar pattern, a moistening patch overlapping with SST warming, and drying patches overlapping with the SST cooling here. And while not shown here, increasing trends in water vapor over the study domain is observed throughout the troposphere with the maximum enhancement near the surface. So to kind of wrap up, we investigated how satellite retrieved macrophysical and microphysical properties of low clouds and the surface shortwave irradiance has changed from 2003 and 2020 in tandem with the significant and robust decrease in AOD over this area. So we found significant changes in low clouds, fewer but larger cloud droplets over the western North Atlantic. However, despite robust and pervasive trends found in low clouds in response to AOD reduction, expected positive trends in surface shortwave irradiance, or in other words, surface brightening, were not found. Given the consistent and robust changes found in large-scale meteorological fields, particularly those correlated with the North Atlantic oscillations, as well as the significant increase in high cloud fraction over this region, which all can alter the radiated environment and thus counteract the surface brightening, we conclude that spatial patterns in the decadal meteorological variability likely set up by North Atlantic oscillation contribute more to the surface cloud radiative effect, especially in the shortwave region over our study domain than aerosol cloud interactions in low clouds. With that, thank you very much for your attention. I'll take any questions or comments.
Okay, thank you, Minnie. Really interesting talk. I'm waiting for a chat question here. I guess in one of your earlier slides, you showed the number of droplets was decreasing over the Atlantic and the particles were getting larger. And the thing I thought was interesting about that figure was that the that one, I think, is an increase in particle size seems to be close to the coast, or the increase in number, or decrease in number is close to the coast, but particles were increasing in size all the way across the Atlantic. And so that isn't really the Toomey effect because the large particles are increasing for some other reason. So you think the particle size is getting bigger because the liquid water path is going up?
Yeah, so that's why we look into the trends in liquid water path, and we didn't see much of the trends, especially over our study domain. And as you pointed out, it's like very interesting because we see the greatest reduction or substantial reduction in aerosols over this study domain, but these cloud number concentration or droplet effective radius responses are not only this domain, this study domain, but extending further to the northeast. So it's interesting, but we don't see much of the statistical significant trends in liquid water path here.
Okay, and let's see, so we have a couple of questions here. Any comment on whether this aerosol effect on base state also appears in the Western Pacific and modes of variability such as a PDO?
Yeah, so even though it's like throughout this talk, I only presented the North Atlantic regions, but we see similar trends, especially in the low clouds over the Pacific, Western Pacific too. And I think these two regions, like the Western Pacific, the west coast of the California and the eastern seaboard of the United States, kind of shares a similar, not exactly similar, but it's interesting, but we see most of the AOD trends only over the eastern seaboard of the United States, but not in the Western Pacific. So I think it might be related to something else or the low cloud decks over there. Yeah, but I observed that from throughout our analysis, and it's pretty fascinating.
Okay, here's another question. Nice talk. Could you calculate the expected surface shortwave change from the aerosol and cloud changes alone and compare that to the observed trend? It would be interesting to see how the magnitudes compare. Go ahead.
Yeah, so even though it's not shown here, I did the simple calculations using the radiative transfer model called SB-DART. So using the numbers from observation from low cloud optical thickness and low cloud effective droplet radius, we tested different ranges of the numbers, and based on that calculation, we expect to see some brightening over this region. But again, when we look into the spatial pattern of the all sky shortwave radiation, we don't see it. So that's why we conclude that there's got to be something that counteracts this effect. Yeah.
Okay, and here's another question. Nice presentation. Can you say something about why there's such a robust positive trend in AOD across the entire southern hemisphere oceans? Your first slide.
Oh, I see. I have no idea. It's like the southern hemisphere aerosol cloud interactions is not my particular expertise. Maybe Michael knows much more about this.
I could speculate a little bit. Since you have 2020 in there, it might also be affected by the Australian wildfires in 2019, 2020. That was a huge perturbation. I think it actually offsets a lot of the COVID aerosol reductions if you look globally. I think there's also been an increase in wind speeds over the Southern Ocean, so there might be a sea salt contribution as well.
Thank you.
I'll just throw in one more question in the last minute here or so. And why do you think the cirrus were changing over the Atlantic?
Yeah, so I think that's related to the more moisture being available to the area. Like when we look into the meteorological responses, we see increase in the water vapor. And as I said, as I presented, this increase in the water vapor is like throughout the troposphere. So not only the low levels, but it exists through the mid levels and higher in the upper level. And I think, I don't know much about the cirrus, but I think it's given that we see the increase in high cloud fraction and that pattern looks like this, it's got to be something to do with the more water vapor being available to the area.
Okay, this is really an exciting talk to think about, and clearly the aerosol effects you can't just talk about separately from everything else that's happening, which is very unfortunate. Couldn't something simple happen? Okay, well, that's the end of our talks for today. I don't know if Ren wants to say something in closing.
No, I don't think so. Just wanted to, I'll echo Brian and say thank you to the three speakers for some really interesting presentations today. Thank you again to Brian for moderating. I was going to mention some of the things that Ben just mentioned in the chat. So there's a chat message with some, with our email address and some relevant links to the activities that we do with the Early Career Committee. So I won't, I don't think I have anything else to add. So just thank you again. And this recording will be available on the AGU webpage. So thanks again.